lecture starts at 10 o'clock again as today, and it will take place in the TH of ITER, which is located not far from there. For those who doesn't know, actually, it is there where we are here. It's in front of the library. And please, don't forget to fill in the list of participants. And at the end, also, I ask you to fill the questionnaire on the lecture. Thank you very much. Professor Fasoli, excellent part.
Good morning. Today I will start discussing a little bit more in the details the magnetic fusion approach, which is what I said, what basically Europe has decided to take. I will show a little set of movies describing the concept of magnetic confinement and the different confinement schemes that we can think of. Then a few words on the plasma heating, how we bring the plasma up to thermonuclear temperatures, how we control the plasma and how we fuel it, and then describe a little bit the main European project at present, which is the jet Tokamak. And then in my view graphs I'll describe what are the challenges in my view that magnetic fusion poses to plasma physics. And today in the first hour we'll attack the issue of the macroscopic equilibrium and stability in terms of a model that's called the magnetohydrodynamics model, and what the stability limits are that model, that description poses to the plasma. What happens if you go beyond the stability limits? So I will start by showing you a set of slides from a CD-ROM, which is, by the way, available for everybody here to take, which is sort of a general introduction to fusion.
What is MHD?
MHD stands for magnetohydrodynamics, and I will describe it later. It's sort of the general description of the plasma as a macroscopic fluid in equilibrium with magnetic field. It's the simplest description of a plasma that we can tackle. So yesterday we have described the inertial fusion approach, which is represented here by that target chamber to which we inject a large number of lasers to make a pellet implode. So we have seen the problems and the issues related to that approach. Today we will go to the magnetic confinement approach. So let's start with the very simple principles. Magnetic confinement is based on the fact that the plasma is made of charged particles, the ions and electrons, for example, here just one species separated. And if you don't confine them, of course they cool by hitting the walls. Now as you impose a magnetic field, they start obviously gyrating around the magnetic field lines, and that's the sort of the basic principle that we have for the confinement. The first approach was to say, okay, we don't want end losses, so let's do what's called a magnetic mirror. I show in a moment what the principle is behind. Magnetic mirror is a situation in which you increase the magnetic field in one location and the particles cannot, not all the particles at least, can escape in that direction. How does that work? I have a separate view graph here. It's based on the conservation of magnetic moment, or at least conservation in a situation in which the magnetic field doesn't change too fast. So it's what's called an adiabatic invariant. A magnetic moment is basically the ratio of the energy in the motion that's perpendicular to the field lines to the field intensity. So the energy perpendicular to the field intensity. So if that's conserved, obviously if you increase B, you also have to increase E perp. But if the total energy is conserved, which generally is the case, then if you have that equal to a constant. As you increase E perp, the perpendicular energy, the parallel energy has to decrease. And at some point, the parallel speed has to go down to 0, and then eventually changes sign. So the particle cannot penetrate further into an increasing magnetic field, and that's the mirroring effect, which can be described by a sort of a force acting on the guiding center of the particles, which means the center of the gyro motion. So it's a way to simplify the description of the motion of plasma particles. And that force is proportional to the gradient of in B. So here is the same thing we just seen on a little movie. A particle goes from a minimum B to a maximum B imposed by external coils, then is reflected. It's exactly what happens in the Van Allen belts here. This is a dipole field of the Earth. It increases towards the poles. So particles gyrate here around the dipole field, and then as they go towards the poles are reflected back. So for example, particles are issued from old thermonuclear explosions, or atomic bombs, I mean. They are still up there because they ionize and they bouncing back and forth. Now, not all the particles are confined in this system. This is why, in fact, it's been abandoned after several years of experimentation in magnetic diffusion confinement, because if you have too high parallel velocity, in other words, you're going too fast in this direction, then you cannot be reflected. That principle doesn't work. So there's a ratio between the parallel velocity and the perpendicular velocity that's critical, and above a certain value, the particles are lost. So in velocity space, that can be seen as a cone, as what we call a loss cone. So if you are within that cone, in other words, you're going too fast along the field lines, then you're lost. And that cone depends on the ratio between B maximum and B minimum here. So you can increase the field here and decrease it here to make it better, or try even to make a field more complicated on this side, but these losses have shown to be too critical for a fusion reactor. So this is a line that was pursued for quite a few years and now is no longer pursued. So the idea was very simple. Okay, let's take the field, and instead of making a straight field, even with mirror, we make it toroidal. So we close it on itself. So we have a set of coils. Here are the set of coils, and conventional or superconducting coils, and the particles would gyrate around these field lines, but all around the torus, so it should be confined. Now, trouble is that if you really look at the particle orbits in such a situation, they're not confined. There are drifts, which I will show in a moment, that will separate electrons and ions. So the ions will go one direction, the electrons will go the other. And that, of course, is causing a loss of confinement. So it's a configuration which cannot be suitable for building a reactor. Why do we have drifts? What are they? Well, again, we take what's called the guiding center approximation, which means we forget about the little motion around the field lines, but we take the center of that motion as representative of the motion of the particle. And in general, just from the Lorentz force, or generic classical orbits here, if you have a force acting on a charged particle, well, the drift that results from it comes from the cross product of that force with the field and depends on the charge. In the case of an electric field, of course, the force is the charge times the electric field, so the charge cancels out and the drift becomes independent of the charge. In the case of a field that's not uniform, in which field lines are curved, you have the drift due to the fact that there's a gradient in the intensity of the field and there is a curvature. In a sense, it's sort of having a force that's a centrifugal force. What happens is that this drift gives you a B cross product with a gradient of B, and therefore in a toroidal device you see that B cross product with a gradient of B will take charged particles up or down, and in fact the charge dependence is there from the sign of the cyclotron frequency, the frequency of gyration around the field lines, which is in opposite directions for the two signs of the charge. So you separate the two charges, then you have an electric field. An electric field brings you back to this situation, cross with the magnetic field gives you a drift. So electric field down, cross with magnetic field, gives you a drift that's outside. So that is very fast and will lose you the particles as we have just seen. So what is the idea to go further than that? Well, we need to somehow make the particles not just go out, but go around in a spiral around the torus, so they experience different sides of the torus and therefore different drifts that compensate. The idea here is to have not just a toroidal field, but a poloidal field, which is driven by a current in the plasma. So let me just go back. Now here is a toroidal plasma. There is a current that circulates in it, driven by a transformer. Okay, I should work like that. The plasma carries a current, so that makes a field around. It's called the poloidal field. So the resulting field, toroidal plus poloidal, is a helical field that goes around. So the particles now can gyrate around this field, but because the field goes around in the torus, as you can see on the other side, then the particle basically experiences both sides of the torus and is confined. This is an example of such a machine, which is called a Tokamak. This is a jet Tokamak. You see these are the limbs of the transformer, which is there to drive the current in the plasma. So in other words, the plasma is a secondary winding of a transformer. So it's intrinsically a non-steady state situation. You have to change the flux through the plasma to drive the current. This is the Tokamak configuration. This is an example of a somewhat modified configuration in which the central part is very thin, so it's called a spherical Tokamak. It's a little bit faint in the picture, but it's an image of the plasma which is subject to this inductive field and therefore is carrying a current around. And in this particular configuration, we have minimized the area occupied by the central, what we call the central column, which is basically the transformer core, the transformer coil that induces the current. It's called a spherical torus. We'll see examples of slightly different configurations. This is just to show an example of a plasma. So the plasma is carrying a current and is therefore confining the particles, removing this problem of the drifts that we have seen in the absence of a current in the plasma. There are other configurations in which the magnetic field is made helical by slightly different techniques. This is so-called the reverse field pinch, in which there is basically a reversal in the direction of the field from inside, of the poloidal field from inside to outside, is related to the turbulence and the dynamo effect occurring in the plasma. It's a configuration that might be of interest for fusion. It's similar to a Tokamak, and it's being addressed in one experiment, in several experiments, but in Europe in particular, in one experiment in Italy. Another possibility is not to drive the current in the plasma to have this combined field, poloidal field that combines with the toroidal field and makes it helical, but to have it driven by external coils. External coils that are they're very complicated because they have to now drive not just a toroidal field, but they also have to make a poloidal field. We need that to remove this problem of the drifts. And so they have to have a very interesting and complicated shape. These are examples of different machines of this kind that are called stellarators. So the twist in the field lines that we need is provided by external coils. The advantage is that in principle they are not subject to the transformer action, so they may be a steady state in a steady state situation. There is very large project being built in Greifswald, which is sort of ex-East Germany. It's called the Wendelstein 7X, and you see it's the demonstrated stellarator concept. Again, the twist in the field lines is given by external coils. You see these external coils look like they've been designed by someone who was was drunk, but it's actually an extremely complicated and high technology problem to design coils this way in order to provide a good twist of the field lines, which in the case of a tokamak is simply provided by the current flowing in the plasma. So this is one line of research that's followed, pursued in Europe and in other countries. Another problem is once we hold the plasma in place, and I'll come back to the issue of the stability separately, we need to heat the plasma. We have two methods, let's say several methods to heat the plasma. First one is, this is going a bit too fast, is by simply having the current flowing in the plasma. The plasma carries a current, the current heats any conductor. Problem is that the conductor is too good. It becomes almost superconducting, so there's very little ohmic dissipation. So we need external sources, and I come back to that. One is by injection of neutrals, and one other possibility is the injection of radio frequency waves, or waves of different sorts resonating with different components in the plasma. These are views of internal antennas. These are Faraday shields for the internal antennas in the Japanese experiment to heat the plasma with in this case, waves resonating with the ion population. Now I'll go back to my presentation for a moment and comment a little bit more about this additional heating issue. As I said yesterday, this is a reminder what I said yesterday, the resistivity of the plasma goes down with the temperature to the 3/2. So the heating by current, as I have just said, in fact, becomes less and less effective at high temperature. At 10 keV, the plasma is an extremely good conductor, and of course the power, the energy per unit volume that you create by ohmic heating is proportional to the resistivity. So at one point you need to come in with a different kind of heating, what we call additional heating. Additional means more than ohmic heating. Ohmic heating is there naturally because we, in a tokamak, we drive a current, but there is a gap between ohmic heating providing the heating of the plasma relatively to low temperature and what will come out from the alphas once we have started the fusion reactions. Here's a plot of the power as a function of the temperature. So we need to heat the plasma this way, and we need to overtake losses. This is the loss from Bremsstrahlung, as we have seen yesterday. As you see in the mid-range here, around a few keV, the Bremsstrahlung losses will dominate over ohmic heating, so we are in trouble there. We're not there yet in a region where the alpha heating may take over, so we need to fill this gap. This is the need for additional heating stated in a slightly different way. There's a gap in the temperature range in which we need to come in with external heating. So I have a couple of examples here. The first example we have seen in a little movie before is what we call a neutral beam injection. So what happens here is that you have a plasma source, so we start from charged particles, which are easy to accelerate. They're accelerated to energies of order of, at present, 100 keV. For bigger plasmas in the future, we need to go to several hundreds of keV up to MeV range. Then they are neutralized in a neutralizer volume, which is in fact very large. It's sort of the biggest volume that you see in the present day tokamak. Then you want to get rid of the particles that are not neutralized, and then you want to inject the neutrals in the plasma. We need to inject neutrals because, of course, the magnetic fields would bend the trajectories of charged particles. So the neutrals come in, they take energy and momentum to the plasma, and they heat the plasma, and they also make the plasma spin if we inject at an angle which may be interesting for driving a current in the plasma or basically stabilizing instabilities by making the plasma spin. One point interesting for technology, this is the neutralization efficiency as a function of the energy of the beam. As I said, in present day devices we are in a range of 50 to 100 keV, so we are still in a range in which we can use positive beams. In other words, before they're neutralized, they're just positive ions. But if we go higher to ranges that are of interest for really a fusion reactor, because we need to penetrate into more plasma and more because there's more density and also because the size will be larger, we need to go to negative beams. And this is an avenue for new technologies being explored both in Japan and in Europe. So when you might hear about negative beams, the reason is that they're not used today because we don't need them. We are still in a region where it's okay. But in the future, we'll be up here, and we won't have enough efficiency in the neutralization to use positive beams. So we need to develop that technology. Another example of heating of the plasma is, I said, by waves. Plasma has collective modes, as I said yesterday, collective behavior. So that means there are several modes of oscillations for the plasma. In particular, there are two species, at least two species, the electrons and the ions. So, for example, you want to heat the electrons, you want to resonate with them. In order to resonate with the electrons, you have to be in frequency, more or less the same frequency as the gyro motion. Because the magnetic field is large, the gyro motion is a high frequency. And the high frequency waves that are used to hit the electrons are in the order of 100 gigahertz range. So that's not an easy range to have high power and long duration sources. And that's why, in fact, the fusion community has sort of developed the sources, or in collaboration with industry, obviously, the sources for heating in that range of frequency. This is an example of what's called a gyrotron tube. It's basically an electron beam that's accelerated at high voltage, and here there's a superconducting magnet with high magnetic field over the 5 Tesla, and of course the electrons gyrate around that and irradiate and emit radiation. That radiation is coupled through a diamond window, and that is the microwave beam that comes out. So this is something we have in Lausanne, not far from here, where we have developed these tubes over several years. It's half a megawatt source for 2 seconds. We have several of them at one frequency, and others are higher frequency. This frequency we resonate with twice the gyrotron frequency, and the other one with 3 times. Sometimes you want to resonate with harmonics of the gyro motion because of some wave properties. This is an image of what a gyrotron looks like in practice. It's sort of a huge cryogenic facility, in fact, for the superconducting magnet. Then once you produce the beam, you have to steer it, and this is not a trivial exercise. These are our gyrotron sources that then you have to steer it all the way to the Tokamak. You are behind a biological barrier here, and then you have to inject it. You want to inject it in this particular case in a very precise way, because you want to be able to heat, and this is one of the advantages of the microwave injection, at a very localized spot where you might need heating, also to cure some plasma instabilities locally, as we'll see later on. So you want an injector that is steerable in both directions to look and inject power at the right spot. You can also inject in a way that's along the toroidal direction, which means by the waves that provide momentum to the particles, you can drive a current, which is what we call a non-inductive current. So a current that replaces the current driven by the transformer. So it makes pulses longer, and eventually may even completely replace the transformer and make the pulse completely steady state. So let me go back to this CD-ROM and go a little bit further into the introduction. I have, unfortunately, to go through the background here. To the introduction to magnetic fusion. This is a summary of the heating methods we have just seen. The beam injector, you see this is jet, and you see the injector with a neutralizing chamber, which is as large as the machine. The current transformer is sort of the trivial one. These are antennas for, again, exciting waves that are, in this case, in the ion cyclotron range. They resonate with the ion population. It's a different kind of problem for what I have shown before. This is sort of a 60 80, 100 megahertz range. And then there's another method which has sort of been abandoned, in fact. It's sort of compressing adiabatically the plasma by moving it by magnetic fields. And the problem with that is that you encounter instabilities similar to what we have seen yesterday in inertial fusion. So the major methods are, again, transformer current, injection of neutrals, and the waves either resonating with ions or resonating with electrons. Once you have confined the plasma and heat it, well, you have to control it. You have to hold it in place with a set of coils. Here is an example of a scenario in which the plasma is vertically elongated by a set of coils. You see that we fire different coils at different times to make the plasma shape. The plasma is a big conductor, so it's subject to J cross P forces. Here is a Tokamak in Lausanne, where we have developed a state-of-the-art sets of control methods. This is the plasma image being taken from a discharge, and the plasma is now subject to active feedback control with the external coils, and you see that it's held more or less in a stable fashion in the right place. So control, in fact, is also an avenue for research, but it is one side of things in which things for a reactor will be indeed easier than they are for today's tokamak, because the characteristic times will be much longer, given by simply the size of the reactor itself.
Could you say where the target where it is and how fast you have to react to this component?
Yes. This is an example, sort of an answer to your question in a sense. Again, this is a TCV tokamak. You see here all sets of coils that are used to act on the plasma. So how do we know where it is? Well, what we need to do is to reconstruct the equilibrium of the plasma. We have an equilibrium, and I'll say a few words about that later on, but at each point, the plasma is in equilibrium as far as the macroscopic aspect is concerned. So there are equations that describe the equilibrium, and they have boundary conditions in terms of magnetic field and current at the plasma edge. So the best we can do in real time is to take measurements of these magnetic fields and currents at the plasma edge, and of course they're related, and then try to reconstruct the equilibrium of the plasma based on those measurements. That will tell us pretty much where the plasma is. In a sense, this is exactly what's shown here. This is a measurement, or should I say a reconstruction of the plasma based on external measurement. And that's fed back to the control system. In fact, there might be even control experts here in the audience. No, he's not here today. That's fed back to the control system and say, okay, now plasma is going too high, fire this coil, and that happens over characteristic times that are tens of milliseconds nowadays, but they will be longer in the future. Of course, they will be longer and therefore easier, but in the case of superconducting coils, it's not so easy to turn on and off the current. So there is an additional complication there. So let me continue to play this movie, because it's sort of from the beginning. It's exactly what's happening. You see the characteristic time here. This is the real time. So it's about 2 seconds total, and you see how the coils are fired, say 100 milliseconds time scale. In TCV, which is Tokamak in Switzerland, because we focus on this problem, we even have coils that are inside the vacuum vessel for very fast reactions. So, of course, if you go through a metal vessel here, the metal can have eddy currents and therefore will slow down your response. So you need to go inside the vessel. This is not necessarily needed for a reactor, but it's good for experimentation of the control techniques. Another problem is the problem of impurities and refueling. I will come back, I think, in the second hour today to this problem. When you see a plasma, this is a nice discharge in terms of public relations from a German Tokamak. But when you see it, it means there is something going wrong, because only impurities can radiate. Impurities meaning not just the fully ionized ions in the plasma and the electrons. So what you see here is sort of a penetration of impurities from the edge. This is not a very well controlled discharge, because you see it hits the wall and it strips some particles from the wall that come in and radiate. So this is another problem to attack. This we'll see later on. One way, another problem, in fact, is to put back the matter in the plasma, so fuel it. One way to do it is to inject a pellet. This is nothing to do with the pellet we saw yesterday. We still call it a pellet. It's sort of a little cube, a little sphere of deuterium, for example, and will be DT in the future, of order of a centimeter, that's injected at very high speed from the side, and plasma around ablates matter from it and basically provides a density source inside the plasma. And how inside depends on the speed of the pellet. So by changing the speed, we can change the penetration of it and therefore sort of try to fuel the plasma locally where we need it. So this is a similar chart to what I've shown yesterday. In fact, very similar. Again, is the product of temperature times the density times the confinement time here as a function of the temperature. You see the different generations of experiments here. Someone said, well, in the 70s you claimed that we were close. Well, in the 70s we were here. So we were orders of magnitude away. But now we are here. We are on the threshold of break-even. And that threshold of break-even has been demonstrated particularly in one experiment, which is the JET experiment, which is in Oxford, England, which is a joint European experiment. So I will show a little bit of JET, which is the project that has been responsible for those points. And these are those points. This is the fusion power over versus time for a few shots of real deuterium-tritium mix. Record being about 16 megawatts of fusion power, with more or less the same power injected in the plasma, a little more. So a power gain of order of 0.7, so say of order 1, which means really close to break even. This is the American experiment that had a short pulse of order 10 megawatt of fusion power. In JET also, other scenarios have allowed to make much longer pulses at lower fusion gain. So this is a sort of record fusion energy produced in a pulse, although the fusion power is much lower than the famous shot here. Here is a picture of JET. Is a big device of order 3 meters, a major radius. It's obviously a toroidal shape, and this is also about 2.5, 3 meters vertical direction and about a meter radius in this direction. You see a person here standing on the floor, and you see that it's all covered by there's metal, and there's also sets of what we call ties. There are particular materials that are chosen to protect the plasma, the machine structure from the plasma power deposited there. And you see different kinds of systems here. This is the radio frequency antennas to inject waves in the ion cyclotron range of frequencies. Is about 50 megahertz again. So we can see a bit more about JET here. Again, this is a general view we have seen. One thing that JET does that at the moment nobody else in the world does is to really work with tritium. It's not at the very moment, but it's been done, in fact, last year with small amounts, and in '97 with large amounts, sort of the real full DT discharge we have just seen. This is a tritium processing plant, a JET. There's not much tritium on the side at a given time, but nevertheless, it's an important technology to develop and to keep alive in Europe as we will go towards a reactor in which tritium will be obviously needed. Another thing which is very important, in fact, I'm going a little bit more towards the engineering side, but it's something that has to be developed, is the remote handling. So once you activate your machine because of the neutrons that 14 MeV come out, you cannot physically go in anymore. There's a little bit too much radioactivity inside the vessel, so you need to do everything by robot. And I think this is one of the most sophisticated robot systems in the world. And I remember when the Hubble telescope had a problem, remember they had to be corrected, they worked together with or at least they contacted for consulting this jet remote handling team, because the sophistication of what they do in the vessel is really extreme. They have a mock-up to real size to do all the tests and then preparation, and then they have this boom which has to install big pieces, but with the sensitivity of a human hand is really an impressive system. And it's a technology, again, it's very, very important for the future. This is finally a video version of a jet discharge, so it's a good discharge. You don't see that much light, it's not spectacular. It's not spectacular because it's good. Its equilibrium is kept quite well. Radiation is only in the bottom where we want it to be. Here there's a little bit of radiation because there's a little bit of an event during high power NBI heating. And this is in a real time more or less. You see the discharge jet lasts macroscopic time, so it's not 1 second, is a order of 30 seconds, depending on exactly what you do, but so say 10, 20 seconds of high power situation. And then I'll stop here, go back to my presentation, and go back a little bit more physics. We don't need this anymore. What I want to do now is to discuss with you the challenges. So having seen a little bit an overview of what the approach is, let's see what the challenges are. The fusion, magnetic fusion I should say, but in fact from now onward will always be magnetic fusion, poses to plasma physics. First of all, we have to handle extremely large power densities and extremely large gradients. The power density in the reactor core will be of the order of 10 megawatts per cubic meter. So that's about 30 times that of the sun's core. The plasma is an anisotropic medium. You see magnetic field, so that makes it anisotropic. And generally, as we have seen from the collisional processes, is not in complete thermal equilibrium. So there's an enormous range of macroscopic instabilities and relaxation processes that can take place. Here on the right-hand side of the view graph, I have put examples of sort of similar problems that are encountered in space physics and astrophysics. For example, the solar flares and the substorms are examples of macroscopic instability of the plasma and relaxation processes. This is a solar flare coming out of the surface of the sun. The plasma is a fluid, but of course it's made of particles. That sounds like a trivial statement, but the problem with that is that every class of particle may resonate with different class of instabilities. So you need to take into account the interaction between waves and particles that can be resonant. You can use it, for example, to heat it, as I described before, but in some cases you don't want it because it leads to instabilities. And it's very quickly nonlinear effect, so it's very difficult to model. All of that happens in space. For example, the heating of the corona outside the sun is believed to be due to wave-particle interaction up there around the sun's atmosphere. Plasma is a turbulent medium because of all the above. And turbulence, we will see tomorrow, leads to what we call non-collisional transport. So the transport of energy and particles is not due to collisions. It's due to interaction between the particles and the turbulence itself. So sets of waves, if you like. An example of that in astrophysics is the problem of accretion disks, in which the star forms and angular momentum has to be somewhat dissipated, and apparently it's dissipated or lost at a much higher rate than it should be by collisional effects. So again, it's probably an example of turbulent transport. Finally, the plasma is kept inside a vessel. Again, this is a jet vessel. So this is a 10 kV or 20 kV plasma. Just outside are the coils, maybe superconducting or not, but in any case, they're very cold compared to that temperature. And it's also very close. So there's a plasma transition here to neutral, first to the wall and then to the outside world, which is very, very critical. The interaction with the wall, how you get out the power that you produce, all of that is very critical. There's some similarities to what happens in plasma manufacturing, for example, on the surface of materials on which plasmas impinge. You can think of modeling some of these things, and of course we do, but there is one major difficulty, and that is because of the nature of plasma of different species, electrons, ions, for example, you have a huge range in the temporal scales, from 10 to the minus 10 to 10 to the fifth, and spatial scales, from microns to very macroscopic scales. So it's very difficult to put all of that in a computer even nowadays. And so you need to have an understanding of the physics that's going on and what particular problem you're studying before you can simulate. The overall system will be too heavy to be simulated. And these four areas we have accomplished progress, and all of this is to go towards what we call the burning plasma, a plasma in which alpha particle heating starts dominating, and so you really start to produce energy. So what we see now in the rest of the course are these four, what I call building blocks, to get to the real thing, to the real burning plasma reactor. We start with discussing macroscopic stabilities. Then we'll have a few words on the interaction between plasma and the wall. And then tomorrow we will look at the transport and turbulence and some issues on wave-particle interaction. So this is sort of a layout of the rest of the course. This is answering your question. I probably don't need to go into too many details. This is how we deal with macroscopic stability. We have a complicated geometry, so we can't afford having a microscopic description of the plasma, or what we call a kinetic description, because the geometry is too complicated if we want to have a global view of what's happening. So we need to go to a simplified model for the plasma, the magneto-hydrodynamic model, which is describing the plasma mass density, rho, the plasma fluid velocity, u, the plasma moves as a macroscopic fluid, and the current density. Current density is very important in a charged fluid. Of course, the magnetic field, the pressure, and that's all, the electric field here in Ampere's law. Now we have simplified the equation that describe the plasma very significantly. And in particular, I draw your attention to this equation, which is just if you like, the E plus electric field plus the term coming from the motion of the plasma, the fluid velocity times cross B. That is equal to 0 if you have ideal plasma. So you say, okay, the resistivity is so low that I put it to 0. Plasma is infinitely conducting. Or, of course, that's proportional to J, and the factor in between is a resistivity. So that's so-called resistive MHD. And it's a very subtle point here, quantitatively, but in fact, qualitatively is very, very important. Again, this is a macroscopic description and describes relatively slow phenomena, so phenomena that are not comparable to the particle motion, because we are forgetting we have particles. We have just the complete overall fluid. And yet it has to be relatively fast compared to the ion motion, thermal motion, so that we take into account the fluid velocity u, but not the particle motion there. The charge density doesn't even appear because we consider the plasma to be quasi-neutral, so there are always enough electrons to compensate the ions. So this is the setting of all these reconstruction of equilibria of the plasma and so on. Now before I go to the practical implication, I'd like to discuss a couple of points on this model. I think they are of interest. In hot plasmas, the resistivity goes to 0. So that means the magnetic flux is frozen in the plasma. The field lines, in a sense, and what we call the flux tubes associated with them assume a meaning as if they were real objects. So you can think of a tube of plasma as a flux tube, because there's a given amount of flux, of magnetic flux in there that you cannot change because the flux is frozen to the plasma. So it looks like a real object. Then you say, okay, how much do I lose if I admit the resistivity is not exactly zero? Because after all, it seems like a very, very, very rough approximation. So we take simply Maxwell's equation in the approach of MHD and take the Ohm's law here with resistivity, then do a little bit of algebra, and you get that the variation of B is due to a convection term. The plasma moves, so it carries the field with it, and a diffusion term. This diffusion term is sort of the separation between the plasma and the flux, which is of course not there if you don't have resistivity. So let's see what's the importance of this diffusion term in cases of interest. And typically one, like in normal hydrodynamics, considers the ratio between the diffusion term and the convection term, and it's so-called inverse magnetic Reynolds number. In plasmas of interest for fusion, and in fact for space, this number is very, very large. So that gives you a characteristic time for the diffusion of B, which is very long, because that's proportional to that number. So in other words, it takes a long time for you to change the flux in a given amount of plasma, or stated otherwise, to separate the plasma from the field lines. For example, if you take the jet tokamak, so this is something that we have today, you calculate the resistivity and you get about 2,000 seconds for that time. So this is much longer than a discharge. So you have to be careful about controlling the plasma, setting right from the beginning, because it's difficult to actually change the configuration in the core of the plasma, at least where the plasma is very hot, over a very short time. So this is another issue for controlling in practice. So let's go back to the issue of the equilibrium of the plasma described by this macroscopic model. Then what you do for equilibrium, you just remove all the tie variations. You're left with a very simple equation, which is the J cross B product equals to the gradient of the pressure. So you want to confine plasma, which means you want to confine the pressure. From this relation, you can see immediately that the dot product between B and the gradient of the pressure, and the dot product between the current density and the gradient of the pressure, they're both zero, which means that the pressure is constant on magnetic surfaces, and the current lies on magnetic surfaces. So every description of the plasma can be done by just saying we have magnetic surfaces. Each magnetic surface can be given a label, which is the amount of flux that it has, a number, and it will remain the same unless something disruptive happens to it. So all quantities are a function of this magnetic flux. So each magnetic surface has a flux. So I say I have, for example, the pressure will be a certain value here, and it will be the same value around this magnetic surface. In the tokamak, we characterize the equilibrium by some quantities. The most important ones are the safety factor. We call safety factor because it's related to some instabilities, and it's, in a sense, gives the pitch of the helical structure of the field. And strictly speaking, is defined as the toroidal angle that covered by the field line to come back to the same position. So if you're here, how long around the torus do you need to go in order to come to the same position? Remember that the field lines are going helical, divided by 2 pi. So in general, Q in the present devices, for example in JET, can be written as the position here, the position inside the torus, times the toroidal field, which is the field along the axis of the torus, divided by the major radius times the poloidal field. That's proportional to 1 over the current. So the larger the current, the smaller this factor. The second important parameter, and very important also in the economics of a tokamak reactor, is what we call the beta, which is the normalized pressure in other words, is a measure of how much pressure of the plasma you can have for a given magnetic field. It's the ratio of the plasma pressure to the pressure of the magnetic field. Magnetic field is what you pay for, and what you pay, and plasma pressure is what pays you back by reacting and making fusion. So the higher beta, the more efficient the reactor. But before we get to the optimization, we need to hold the plasma in place. So we need to see what the limits are that are imposed by this MHD model. Now, not only do you have to have an equilibrium, but you have to have a stable equilibrium. And that comes in a bit more complicated math, so I decided not to go through that. But I will discuss a little bit what the limits are that are coming from the need to have a stable equilibrium given by MHD model. In general, what do you have? You have destabilizing forces. As I said before, we have gradients. We have gradients in the current. The current is not the same everywhere in the plasma. In this core, we have generally more current. You have gradient in the pressure. And you also have what we call a bad curvature, which means the edge of the plasma on one side is subject to hydrodynamic instabilities of the same kind as Rayleigh-Taylor. The curvature of the field acts as a, if you like, as a force or as a gravity force in the case of two fluids impinging on each other. So there are regions of the plasma which are prone to that instability. Other regions which are actually not prone to that instability, where we have so-called good curvature. These are the destabilizing forces. The stabilizing factors that we can try to use are the fact that the field light bending and compression tends to be avoided by the plasma. So in other words, you need to spend energy to bend the field lines. The field lines are like guitar strings, are subject to some tension. So if you are smart enough that you make a situation in which the instability, in order to grow, has to bend the field line, well, you reduce the growth of that instability, or maybe you even can get rid of it altogether. And as I said, there are regions of good curvature that are not prone to this instability. We can divide the instabilities into two classes. What's called the ideal MHD instability would be an instability that doesn't need to have a resistivity, so it's in an ideal plasma. And because of that, it doesn't change the structure of the field. It doesn't try to decouple field and plasma, so it acts over very fast time scales, microseconds. So in that case, in practice, we have no hope for an active control. So we need to just not be in an unstable situation. There's nothing we can do about that. It's too fast. The second class is a class of instabilities that are related to trying to, if you like, decouple the plasma from the flux. So they're related to a finite resistivity. And because of that, we've seen that it takes some time for the plasma to be decoupled from the field lines. These take a much longer time scale. So here we do have hope for actively control. If we know where they are, if we know what to do from the outside, we can have time over such time scale to do something to control them, maybe limit their amplitude, maybe just get rid of them altogether. Why do we care? Why do we always try to be on the edge of these stability limits? Well, because the stability limits impose limits to the optimization of fusion parameters. So in other words, as we optimize fusion parameters, we are going naturally to hit all of these limits. So we just have to stay a little bit before the limit. For example, there's a stability limit in the current. You cannot exceed a certain current for a given field. That in itself limits the energy confinement time, because the confinement will go basically proportional to the current for a fixed field. What can one do about that? Well, modern approach is that you can improve the situation by making the plasma shaped. In other words, having a distribution of current that's slightly different from circular. So you push the limit a little bit further. In fact, I have an example of that. Here is what we do in Lausanne. You have here is the elongation. In other words, how much we stretch the plasma cross section. And here is basically the current is sort of normalized, but it's the current in the plasma, and you can increase the current yet staying within the stability limit if you increase the elongation of the plasma. And you have here a plot of the beta that we can reach, this ratio of the pressure to the from the plasma to the magnetic pressure as a function of this current. And we have extended all the points here to the stability limits by sort of modifying the stability curve using shaping of the plasma. So this is an approach that's now quite well followed in different experiments. There are limits in the beta, in the normalized pressure. As I said, this is very important for the economics of a reactor because the fusion power is proportional to beta square. So if we're limiting in beta, we're limiting in fusion power for a given field, and the field is expensive to produce. Again, even this one can be improved by shaping the plasma. There's also limiting the density. This is not entirely understood, or at least the exact formula for where the limit is. And obviously the density limits the fusion power also severely because its fusion power is proportional to the density square. We're still working on understanding what the causes are, but it can be improved by playing with the profiles, having profiles that are more peaked. In other words, larger pressure, for example, at the center than at the edge, and that ratio may be very, very large. So this is an example of all of these words translated into a graphic, at least for the beta limit and the current limit. This is a variety of existing experiments, and I didn't even put the points here because it would be very messy. So these are the regions where the stability is found, and the points in which you can operate the plasma safely are indeed within those limits. So ideal stability limits are quite well understood with the caveat of the density limit, but the limit that are most important are the beta limit and the current limit, and they are quite well understood, so we know how to stay within those. Now what happens if you don't stay within those, if you make a mistake, or if there's another limit that comes in, for example a density limit? It's not always completely trivial to predict. There's an empirical scaling, but it may be different in a completely new experiment somehow. So what happens if you're going beyond these limits, if you're hitting them? Well, then a problem happens. You have what we call a disruption. Disruption is a sudden loss of stability, you're outside the limit, which means the plasma collapses, and the current that's carried by the plasma also collapses, and they do that over a very fast time scale. This is an example from jet. Jet runs up to several megaamperes of current circulating in the plasma. So millions of amperes here are suddenly lost because there's a loss of stability here. So they're suddenly lost so fast that in this graph it was probably just one point. So this is always recognized as a problem. There's been a lot of progress in this. Yes?
Does this loss result in damage because there's a lot of power?
I will discuss that right now. And then I'll stop for a little break after these points. There are several consequences of the disruptions, to answer your question. First of all, before even we get to the power itself, there's still a lot of voltage that can be there. So you're driving a lot of current with a very, very good conductor. Suddenly that conductor disappears. What happens? Well, you have a sudden increase in the voltage. And that voltage is represented here. It's not the same everywhere, but let's say this is the loop voltage up to 400 volts for a 3 megampere disruption. This is a zoom in the time scale, by the way. You see that happens over tens of milliseconds here. The current is disappearing here to zero. It's negative current, so it looks like it's increasing, but it's actually disappearing to zero. The loop voltage is left there, but you're also left with some charged particles. There are still electrons there. So what happens if electrons are subject to a strong loop voltage? They are accelerated. Remember collisions theory, a little bit of that we've done yesterday. The cross-section for collisions goes down v to the third power. So if you increase the velocity, you will become less and less collisional. If you're less and less collisional, it'd be easier and easier to increase the velocity. So you're going what's called a runaway electron regime, in which the electrons are basically indefinitely accelerated. Obviously, they reach relativistic energy and so on. But even before they do that, they start being lost because it's now difficult to confine relativistic electrons by a magnetic field, and they hit the wall. If they hit the wall, they carry a lot of energy, and there may be significant damage. Point number one. Point number two. Actually, before I come to point number two, let's immediately see how you could get rid of that, because it's a very critical issue. This is an example of what we call disruption mitigation. So you know the disruption is about to happen because you reconstruct the equilibrium, suddenly it goes very strange. What do you do? For example, you inject a puff of helium. A puff of helium is there to basically make the electrons collisional again. And if you do that very fast, the runaway electrons are slowed down or even prevented from being created at high energy. And so here is a time. You inject the helium puff here, and you remove the effect of the runaway electrons. So you observe the plasma equilibrium is about to disrupt, you're crossing stability limit, you inject the helium puff, and you prevent the runaway electrons from being produced, and therefore you prevent the direct impact of those on the wall. But as I said before, that's only one aspect of it. There's a lot of current going in the plasma. Where does it go once the plasma dies? Not all of that goes into the runaway electrons, especially if we are smart enough to prevent them from existing. The plasma carries current and is moved very fast, for example, up, or it can be down by disruption. In this example, is sort of up to the right-hand side. This is a jet cross-section, by the way. And it carries what's called a halo current. So the current is sort of running around the edge of it. And that simply hits the plasma, the wall here, the machine wall. And it's a lot of current. It's about 30%, up to 30% of the plasma current. So up to 30% of several millions of amperes. It's a lot of current to circulate in the objects around the plasma. So we need to take that into account. We have to design according to that. Another problem is that you have a nicely organized colloidal field structure. This is the equilibrium that we have created. And then suddenly that's lost. And that's lost over a very fast time scale. It means that there's a lot of field that changes. When you change the field, the ability in jet is up to around about 100 Tesla per second. And it's in both radial direction and colloidal direction. Here is before disruption. This is just after disruption. So you see there's a lot of field that's changed. So that means that you have an enormous amount of available flux change to induce current. So what you really want to avoid is to have loops that can carry the current induced by this enormous amount of flux change. So we need to be careful about not producing runaway electrons. We need to be careful about halo currents, and we need to be careful about possible path for induced current to exist. If we're not, then the current that's induced either by halo current in the plasma or by this colloidal field change, then we give rise to enormous forces, because the B field is still there, so J cross B will give rise to enormous forces, and there are lots of stresses. When there's a disruption in jet, and nowadays we produce them to study, for example, mitigation effects, because we know very well how to avoid them in general. Well, the whole machine, which is I don't know how many tons, moves up and down, then back by a few centimeters, and you can even hear it. So it's the enormous amount of force that's being, and energy that's being dissipated in a short time. So here is the end of my first part for today. So we can stop for a few minutes. Maybe we can start. So what time do we reconvene? Maybe up to you.
Since it is already 10 past 11, say 5 minutes.
So a quarter past 11 we start again.
Have a